I will shortly introduce the first speaker, who is Javier Goicoechea, MERLIN's technical leader. Javier is an engineer from the University of Navarra. Since 1997, he has been working at the Research and Development Department of CAF, supporting CAF's Chief Technology Officer. Javier will also be the technical coordinator of Shift2Rail, the Shift2Rail Lighthouse project, Road to Rail, that will be starting in May next year. So he started already, okay. So, and I think we have a little surprise.
No,
yeah.
No.
Oh, you will introduce it. Okay, thank you, Javier.
Yeah. No, this one. Okay. So thank you, Isabel, for your introduction. I am really pleased to be here today to present to you the results of our project that started more than 3 years ago. So after an incredible amount of work carried out by all the partners, today we can show you some results, and I hope that you appreciate and enjoy what we have prepared for you today. But before I start with my own presentation, I would like you to show an introductory video that we have prepared for this final conference.
Energy efficiency in railways has been increasing in the last years, thanks to a number of factors such as improved components or subsystems and new deployed technologies. Unfortunately, this type of costly mechanisms cannot provide further and significant reductions, although we believe that electric railways have still a great potential for further improvements in efficiency. On top of that, minor changes in the baseline scenario, for example new vehicles, fluctuating price of energy, different timetables, will have for sure a big impact in the optimal solution. The goal of reducing energy consumption locally may not be the best one from a system point of view, because of a number of cross and side effects. This is the environment where MERLIN project was conceived and launched 3 years ago. MERLIN was co-funded by the European Commission under the FP7 program and coordinated by UNIFE, and it gathered more than 20 partners coming from the rail industry, infra managers, railway operators and research centers from all across Europe. The ultimate goal of the project was to investigate and demonstrate the viability of an integrated optimization in order to achieve a more sustainable and intelligent management of energy in the electric railway systems in Europe. In that sense, the project has addressed the integrated energy management in several traffic scenarios. For example, high speed, freight, regional, commuter and mixed freight passenger. MERLIN relied on an integrated optimization approach that includes multiple agents, dynamic forecasting supply-demand scenarios, and cost considerations, and all of these in order to support the strategic and operational decisions. Once implemented, the MERLIN solutions, some of which were tested along the 3 years of the project, will enable an overall reduction in energy consumption at system level of 10% by 2020.
So after this nice video, I will start my general presentation of MERLIN. Well, MERLIN, it's all about electricity. Electricity is part of our lives. We know electricity since we were born. Electricity was a fundamental part of our toys when we were children. Our toys were powered by electricity. Even today, our toys are powered by electricity. I mean, with toys, this kind of toys we are using every day. So you can imagine how strange and how, it was like magic in mid-ages to have this kind of power. And only wizards like MERLIN were able to produce electricity at that time. So we relate electricity as a green energy, a green source of energy, just because we don't see smoke coming out from our mobile phones and laptops. Well, sometimes it happens, but in general, we don't see the smoke like the smoke coming from a exhaust pipe of a car. But that is not really true. I mean, still in railways in Europe, 81% of the produced electricity comes from non-renewable energy sources. In other words, it is produced by power plants that emit pollution, but also generate radioactive waste in some cases. So, and the tendency, even if it's, as you see in the little graph there provided by UIC, in the handbook, you can take some examples there. It's very interesting. The tendency is to increase the amount of energy produced by renewable sources, but still we are far away to have the majority of the electricity coming from those. Energy has also a social dimension too. More and more, the topic of energy or fuel poverty is on the spot. You know, there are a lot of European citizens, around 11% of the people that suffer from energy poverty. What does it mean? That they have, at the end, they have difficulties to warm up their houses during winter period. And the problem is not only the lack of comfort for them, but it is also causing additional costs in the health system. So this is paid for all of us. So the point is that we cannot railways cannot afford wasting energy. And we have great potentials, as we said before, to save energy, to save electricity. So this is also this kind of social spirit that we must keep in mind. So how can then railways contribute? Well, railways started a fierce fight against energy consumption time ago. Okay, railways were pushed by the greener and greener cars and buses. The car industry in general, they were pushing forward to have more ecological vehicles. So in order to keep as the reference in terms of efficiency and green mode of transport, railways started a lot of activities, a lot of research projects and technology developments, as you can see here, to keep this nice position as being the nicest, greenest mean of transport. But nevertheless, despite these big efforts made so far, the specific energy consumption is too high. So we haven't seen a big reduction, as you can see in also this nice graph provided by UIC studies. So we still have around 400 kilojoules per kilometer, passenger kilometer. That means 110 watt-hour per passenger kilometer in passenger transport. So, and even worse, as you also can see, the tendency is to keep the values. So we are spending a lot of money in individual technologies, but the results at the end of the day are not so clear from this perspective. We have also nice values to see that interesting, at least as the annual consumption of railways in Europe is 36 6,000 gigawatt hours, which is a lot, especially if we compare that this is more or less the consumption of 3.5 million families in Europe. So just with what we are consuming, we can provide the energy for this amount of people, which is a lot. Especially if we remind that we have 54 million citizens, European citizens, that suffer from energy poverty. In addition, we have another aspect, which is the market liberalization. So this brings a new scenario where the railway undertakings may purchase energy to different suppliers, so open the door for new strategies and new ways of understanding the business models related to energy. So, if we go to typical energy flow, these sunken diagrams, this is for suburban, but its figures won't differ much from other sectors, other types of vehicles. We can see that there are some energy losses somewhere in traction, in auxiliary loads, but also we have important losses in other areas related to the braking, and also the losses through the transmission of the energy. So if we focus on the components, so to say, that we see that we need quite amount of money to improve. We are, for example, some companies here sitting around the table today, we are spending a lot of money now, in the past and in the future, for example, to develop new traction systems based on silicon carbide semiconductors. But we are spending millions of euros just to probably improve the efficiency of the traction by 10%, 20%. This 10% at the end, if we look at this diagram, means less than 2% of the overall energy consumption. Okay, so we think that there are also other means to reduce this energy consumption if we tackle the other branches. So there are a lot of energy which is still burned during the braking phases, that are burned because of lack of efficiency of the system, lack of coordination between the different agents. So in that sense, we think, and that was one of the motivations of the project, that with, in comparison, lower investment, bigger reductions in energy consumption could be achieved. So MERLIN, at the end of the day, intends to cover both aspects. We want to play with the flexibility given by some developments at component level, but also with the improvements coming from the system level. So tackling, as I said, the braking process of the train, coordinating the different agents in order to have an integrated approach. So this integrated optimization approach is based on the vehicles. The vehicles are, of course, the main consumers of the system. So we have the different types of vehicles: regional, high-speed, suburban, freight, and so on. So we have to integrate them in the management system, in the smart grid. We also have other components, which are the traffic control, the timetables, so how the vehicles are dispatched. So this is also an important factor, as we will see later today in the presentations. So this is another factor, another actor to be taken into account in this integrated approach. We also have the infrastructure. The infrastructure is very important, not only because it is where the trains are running. So they have their own characteristics that must be taken into account in the process. It's different if they are hills or not. There are crossings. Well, there are a lot of aspects that may or must be taken into account. Also, the consumption of stations. Stations may be included in the game. Of course, we have the power supply. It's very important. Power supply, not only by having, for example, reversible substations, but also energy storage systems that will provide the needed flexibility. So how to control, how to manage these concepts and systems also must be put in the equation. More and more, the infrastructure managers are installing own renewable sources components in order to take an advantage of green energy. So this also injected in the system, maybe just for feeding the stations or auxiliaries, but must be taken into account if we want to implement a smart grid. And finally, last but not least, the money. I mean, the contract, the business cases behind. These kind of technologies, we are talking about energy storage systems, reversible substations. They are not cheap at all. I mean, there must be a business case behind that supports the investment of the infrastructure managers in such technologies. And if we also intend to, so to say, involve the trains with some new components, that means that there must be some benefit for the train operators as well. So we, in the project, we haven't forgotten the business case at any time, and this is one of the main factors for us. So to summarize the main goals of MERLIN, we have defined 3 missions. The first mission is to optimize the energy consumption, the energy needed to run the system while fulfilling the timetable, for example, to the requirements. Also to optimize the power demand. It means to reduce the peaks, to suggest reduction in the power contract, for example, to smooth how this power is delivered, always, again, keeping the promised performance of the system, and finally, again, the cost. This is the third main factor for us, to allow, to promote, to sponsor the deployment of such technologies. Cost is always in our mind. So today we will show you the 2 main tools that we have developed. They will be presented in the next minutes by my colleagues Roberto and Valeria. They will go into the details, but just as a short summary of them, the first is what we call strategic decision-making tool, which is an offline tool in order to optimize a network from a strategic point of view. So focused on investment for the future, so to decide what are the best options in terms of the different parameters, design parameters. This is very useful for either refurbishment of a line, upgrade of a line, or for new lines. And then we have the online tool, which is it's to be called as the REMS, the Railway Energy Management System. And this is our proposed smart grid for railways. So it works in real time with the different components, different agents. And, well, you will see, again, you will see details about both tools in the next 2 presentations. So from my side, this is all so far. And I hope you enjoy the presentations, the next presentations. Thank you very much.
Thank you, Javier. Let's now welcome our second speaker, Roberto Paracin, who is a senior research associate at Newcastle University, where he leads a working group of the Center for Railway Research. This Center for Railway Research is called New Rail. In Merlin, Roberto has been the work package leader of the work package involving the development of the strategic decision-making architecture and tool, as well as its implementation in the UK mixed traffic scenario. So the floor is yours. Roberto will present the strategic MERLIN methodology and process. There you go.
Thank you, Isabel. Okay, so good morning. So we had quite a lot of introduction, so hopefully in the next 15 minutes I will give you a bit of a flavor of some of the work that we've been doing during the last 3 years or so. So I'm going to present you, as Javier just mentioned, the approach is twofold. We have a strategic approach and an operational approach to the work that we've been doing in Merlin. So I will present you the fundamentals behind the strategic approach that we follow that has resulted into the architecture and the tool that we prototype for this project. Oh, that was quick. So the objective of this tool and this strategy was to develop, as you can see there, a decision support approach that will guide the user, and this is important, it will guide the user, it will not give you the final answer, you need to work it out, so it's just an advice. So it will guide the user to try to develop strategic decisions that will find this trade-off or find an optimum trade-off between the capacity, energy optimization, and competitiveness, and I will talk about that trade-off in a second. But the first thing to think of, the first thing that we actually thought about before we started the project and when we started doing this work, the strategic work, was what is energy efficiency? And the immediate answer is complex. It is very difficult. It's complex because what we're trying to optimize is not a simple function, is a very complex system. The railways is one of the most complex systems you can face, and therefore energy optimization is not straightforward. So immediate thought could be that what can you do with a given amount of money? So as I say in there, what sort of can be achieved with a specific amount of money? So passenger kilowatts per passenger kilometer or ton kilometer or something like that. But that will not look at the whole issue. That will be looking in isolation at energy. But sustainability, if that is the goal, transport sustainability and the role of the railways, we thought that there's a twofold strategy there. So on one side we have the trying to optimize the energy to maximize traffic flows. Okay, so that will be one part of this strategy. But also we need to achieve high loading factors on those very high traffic flows. Otherwise, we are not really fulfilling the objective. So if you can think, a lot of engineers in this room, so you can give me the most efficient vehicle you can come up with, and give you challenges, come up with whatever. If it's running empty, it's not efficient. It's not energy efficiency because you're wasting. So you have to have this sort of a strategy. So this is the kind of framework, big general framework that we were considering in this work. But there's another challenge, which is the trade-off, as I mentioned earlier on, which is at the core of this work in this project, and from the strategic perspective, this balance between energy optimization, capacity, and the competitiveness, the service that you provide. And unfortunately, these three elements are not aligned. They have a tension between them. There's a tension between. So if you try to optimize energy, chances are you're probably going to penalize your offer or your capacity. So if, for example, if you think about a high-speed service, we could easily optimize the energy by reducing the maximum speed from 300 kilometers an hour to 250. that will mean that the service you're providing is longer service, so it's not that high speed. You don't have that quick connection, for instance. Instead of 3 hours from Madrid to Barcelona, you might spend 3:45. That might be not as attractive. So you're losing in the other one. So you need to find a balance, and there will be capacity implications, of course. So trying to find that balance is at the core of the challenge and the complexity of this methodology that we're trying to implement for strategic decision making. So I promise this is not a lecture, but I have to touch on the basis of it, on the science underneath all this. And probably a lot of you are aware of these methodologies, but this is what we actually used to develop the strategic decision-making architecture and the tool that is based on such architecture. So it's two methodologies that are complementary. In fact, the first one is part of the second one, so it's the multi-objective optimization. So I've been talking about this trade-off, this tension between these three elements. So it's a multi-objective optimization. We want to optimize those three to find a balance. So also called MU, if you want. So we look at the different variables and how we can optimize that. But there's also the MSDO, okay, the multidisciplinary system design optimization, which follows a process that includes the other approach. So that's sort of a summary of the process, and it's a very simple process in principle in terms of conceptually. The first phase, you have such as design, a number of design vectors, effectively the configuration of your system, how the railway system, what do you want to design, or we want to design, looks like. Then we have, that is multidisciplinary. There's different disciplines to this. You have infrastructure, you have civil engineering, you have electrical, mechanical, economics, also different disciplines. We have a box, an area where we actually have different discipline models that use those design inputs in terms of creating the design of the system and the output, so what the system configuration will look like. So that's our first phase. We have our configuration. Then we need to analyze that. We need to evaluate that. So the second phase, which is the bottom part of that graph, looks at evaluation, looks at the outputs of this design, and tries to find the best or the better performance parameters, and goes into this multi-objective optimization, which includes the use of a number of algorithms, and you can choose a number of them, and you can be more than one. And that will create a new configuration, a better configuration of the system that then gets input, and so on and so forth. So you have a loop in there until your final evaluation creates a configuration that cannot be improved anymore. So that's the principle of this methodology, and that's the one that we used, and is currently used in many complex systems to look at strategic decision making. Okay. In terms of the MU. Basically, we chose a genetic algorithm because the literature shows that is the most appropriate for this sort of complex situation. We selected, or we decided to use a Pareto optimal solution finding rather than a fitness function approach, and some non-nominated solutions. And I'm not going to go through all that because then I will start to look like a lecturer, and this is not the aim of the presentation. But just very, very simple. If you have two functions, so let's say energy cost versus energy consumption. So the first one is very easy. You don't need a model for that. Solution one is better in terms of cost and consumption. So easy, you choose that. The second one is a bit more tricky because solution one is better on cost, if function one is cost, but it spends more energy. And the second one spends less energy, but it's more expensive. So which one do you choose? But then we get what in reality happens, which is the far right, where you have an awful of population of solutions, the blue crosses, where it could be optimized. Each one of them could be actually better. But we will arrive to a number of solutions, the red crosses, what cannot be improved. So those solutions will give us the optimum Pareto front kind of thing that we were talking about. So that's what we've been aiming for. Now, this is for two functions. When we have 6 functions, like in some of the scenarios that we've been doing in Merlin, the thing becomes far more complicated. So what we try to do is use a ranking system, okay? And I'll leave it like that. We use a ranking system. I'm not going to explain that one. So what it means, this is the basis, this is the sort of the fundamentals behind what we've done. So what we actually have done. So we've taken all that, We look at the problem, we look at the research that we wanted to do, because you have to remember this is a research project. So we wanted to explore what that could take us to. And we came up with this, not just the drawing. We're not just been drawing all the things behind this, of course. So let me just, oh yeah, it works. So this part here is the tool. It has 3 different modules that we have developed, software modules. Basically, this is the bottom part on the strategy that I showed you earlier on, the optimization, where it might be a bit difficult to read, but over here is the optimization algorithm module, which is self-explanatory. It does what it says on the tin. We have a contractors arrangement module that looks at all the cost-related aspects that we want to perhaps optimize, and we have a interface, a core module that acts as a processor of the outputs of these operations and the existing models, which is the top part of that graph that I showed you earlier on. In the case of the project, this is basically multi-train simulators, okay? The multi-train simulators are either commercial or owned by the different partners in the project. So it's basically a black box. We cannot do anything with it. So this is what we kind of the basics of the architecture and what we base the development of the tool. So summarizing, so hopefully I'm doing all right with time. Javier mentioned 3 missions. We actually added an extra mission for the strategic dimension to it. So we have 4 missions to fulfill. We identify and develop 22 functionalities for the tool to complete. There's an example there of what functionality will do. So the software that we developed, or the different modules that we developed, should fulfill these functionalities. So this is a software specification for this. And as I mentioned, we have 3 models and, 3 modules. And this has been used in all the scenarios that we use, apart from 1. So in 4 scenarios that you will hear some results in a few minutes, have used this tool. Okay, so I think that's all. So thank you very much. Questions?
So, in terms of punctuality, we are actually ahead of time. We are 15 minutes ahead of time. So we'll welcome the 3rd speaker, Valeria Bagliano, which I will shortly introduce. I just wanted to tell you that we're gonna take time for question and answers after Valeria's speech. So if you have questions to ask to the other speakers, please don't hesitate. Okay. So, Valeria is an engineer in computer science. She works for the Transport Engineering Division of Da Polonia, an Italian consulting and engineering company. Within Merlin, Valeria is in charge of leading the work package on reference architecture for smart energy use, and also the work package on energy efficient components and energy management technological solutions. She's also involved in work package 7 recommendations for market uptake and implementation and standardization. So Valeria will present the Merlin operational methodology and process. The floor is yours. Okay.
Thank you, Isabel. Good morning, everybody. So, as Isabel said, main objectives of this presentation is to describe the MERLIN operational railway energy management system, which has been developed by the MERLIN consortium. So, the MERLIN operational railway energy management system is an integrated tool and solution aiming to optimize the energy consumption inside the railway system. Specifically, in this presentation, I'm going to show you the architecture of this system and how the system has been developed and designed. The system has been then implemented and its validation has been done through some use case scenarios that will be presented today later on. And specifically, the part related to the operational railway energy management system has been implemented in scenarios 1, 2, 3, and 5 that we will see later on. So now, sorry again. Okay, sorry. This slide represents the general concept which is behind the operational railway energy management system architecture. This is the general view of the system, and the different details on each subsystem will be presented during my presentation. So basically, the energy management concept is represented through 3 operational modes that have been defined for the system, which are the day-ahead optimization, the minutes-ahead optimization, and real-time operation. So this structure was decided during the definition of the architecture because the optimization is performed by the system at different levels, both in time and location. So at network level, in the upper part of the diagram, you can see that there is a high-level optimization, which takes into account the power estimation profile for the next day and all the infrastructure and operational characteristics and constraints of the whole network. For example, the timetable, the railway distribution network characteristics, and so on. But also the distributed energy resource estimated generation and external consumers' power estimated demand. So characteristics of the internal to the railway system, but also external consumer and distributed energy resources. Then at local level, we have a minutes-ahead optimization. So in each zone of the network, we take into account the optimum power profile calculated at day-ahead level, and we perform a minutes-ahead optimization, usually for the next 15 minutes, for each different zone of the railway system, where each zone is defined geographically and taking into account the presence of at least one intelligent substation inside. Then we have finally a real-time operation actuating the calculated time slot profile for the considered zone coming from the minutes-ahead optimization. Sorry. Okay, so now I'm going to detail a little bit more the main blocks of the system architecture for the railway energy management system. First of all, we have the interaction, the interface with the electricity market. And this is performed by a module which is called Electricity Buyer Decision Maker, which have the main objective of optimizing the short-term electricity procurement. So specifically, this module of the railway energy management system determines for each hour which is the amount of energy that is to be purchased and sold by means of contractual arrangements, and which is the amount of energy that is negotiated at each section of the spot market. Then we have another big module of the system, which is the global optimization system, which performs the wayside optimization for the whole network and calculates on the basis of the whole network conditions the optimal power profile for the following day. We have a local optimization system, which starts from the inputs coming from the day-ahead optimization. It means from the global optimization system for the whole network, and determines the optimal power profile for each zone in a minutes-ahead interval. And finally, as I said before, we have implementation of the actions that have been calculated by the optimization. And so we have the dynamic onboard energy manager, which reacts dynamically to the indication received from ground and provides to the DAS recommendation for performing an efficient driving of trains. So, for the definition of the railway energy management system operational architecture, an important support came from the Sensenelec ETSI Smart Grid Coordination Group, who provides a smart grid architecture model that has been reused and, of course, adapted to the MERLIN system solution. This has been done mainly in order to fulfill the smart grid standard models and to develop also a generic architecture which can be in line with the state-of-the-art solution in the field of smart grids, of course, taking into account all railway domain constraints. These slides represent the generic architecture of the smart grid architecture model that we have used as a reference, as I said. And this is, as you can see, it is a three-dimensional model which has 5 interoperability layers on the left part, representing the business objectives and processes, the functionalities, the information exchange and data models, the communication protocols, and the components of the system. And each layer covers the two-dimensional smart grid plane, which is better detailed here. And it is composed by domains and zones. So, zones represents the hierarchical level of the power system management. So, from process, including the real transformation of energy, up to the market. Domains, instead, are physically related to the electrical grid, and they cover the complete conversion electrical chain, from the bulk generation to the customer premises. For what concerns the MERLIN project, the railway energy management system functions and components have been positioned in the smart grid architecture model plane, as I will show you later on. So basically, we started from the smart grid architecture model, and we identified, first of all, the 5 interoperability layers. The first one is the business layer, which means the business processes of the system, and in this case we have identified the 3 main missions and objectives of the railway energy management system that Xavier described before, and I will show you them again later on. Then we have a function layer, which includes all the functionalities of the system for each of the so-called operational mode. It means the day-ahead optimization, minutes-ahead optimization, and real-time operation. Then we have the information layer, defining all the information and data exchange and the relevant data models. We have communication layer, including both smart grid application communication standards and railway domain protocols. And the last layer is the component layer, including all the components, it means hardware and software modules, which implements all the system functionalities. So, Starting from the smart grid architecture model, we have defined this 5-layer in order to be adapted to the railway domain. So I start now to analyze a little bit more in detail each one of them. This I will present quite quick because it was already described before. So the main missions of the railway energy management system from the operational point of view are 3, and are the optimization of the energy consumption, the optimization of the power demand, and the optimization of the costs relevant to the consumption. In all cases, taking into account the operation of the railway system to ensure the fulfillment of all the performance requirements for the railways. Then we have the function layer, the second layer. Here you can see the functionalities, the high-level functionalities that we have defined for the system, because then for each of them we have a lot of more detailed function with all the data exchange between them. But here you can see the main functions, and specifically in the upper part you see the function related to the day-ahead optimization. So we have the day-ahead optimization itself, which is the function that calculates the optimal power profile of the whole network for the following day. But we have also some functions which are related to the electricity market. As I said before, there is a specific module, which is the electricity buyer decision making, which performs energy trading and billing. So energy trading consisting in determining the best price to buy energy, and billing to calculate the real cost of the consumed energy. Then in the middle of the plane we have the minutes ahead optimization function, which performs the optimization of the different zones for the next minutes. And we have also 4 functions which are implementing the real-time operation. So different function to acquire the real-time status of trains and all other components of the system, such as energy storage systems, substation, external consumers, and so on. And to send suggestions to each actor to implement the actions that have been calculated during the optimization phase. So for each of these functions, we have analyzed in detail all the inputs data, the source of this information, and which are the output data and the destination components. Then we have the information layer, which basically shows the data which are exchanged between all the functions that have been presented before. In this layer, we have identified the RailML as the standard language to be used for the communication exchange of information. This is because it's a language for interoperability that is very commonly used in railway industry applications, and so it was agreed that could be the best option for our system. RailML did not contain specific information on energetic aspects. Therefore, inside the MERLIN consortium, an analysis has been performed to analyze which are the information that could be useful for the MERLIN solution, and minor extensions of the language have been foreseen in order to be compliant with the MERLIN system architecture and taking into account all the information that we need for the system architecture. We have done the communication layer, which consisted and provides the communication protocols and the mechanism for the interoperable exchange of information between the actors of the railway energy management system. So the analysis was done on protocols used in the railway domain, as well as on protocols used in smart grid applications. So basically, main common protocols used such as the EIC 61375 of Train Communication Network and the EIC 60870/5 have been selected, as well as many other protocols already used in smart grid application and in the electricity domain. And in some cases, as it is a research project and we bring some new components, we also have the option and the need to use customized protocols because they are not yet present on the market. Finally, we have the component layer, which represents all the components in the form of hardware, software, and interfaces to implement all the functionalities of the system. As you can see in this small picture, we have identified a lot of components which have been allocated to the smart grid architecture model plane, as it is shown in this slide. So, thank you for your attention.